Yeah, he's a student in Marseille at IFE and UST. Yeah, I see. And he works on cardiovascular biomechanics.
Thank you. So before beginning, I would like just to thank the organizer to give me this opportunity to present my work. So yeah, so I'm a PhD student in biomechanics. So I want you to forget a bit about like geology, soils, and replace the rock by a more complex porous media, which is named the intraluminal thrombus, where thrombus is like a complex word to say blood clot. And like the second thing is that I do blood clot.
Oh.
And the second thing is that I do experiments on real human sample, okay? And in the first slide I will put like a little bit of disgusting picture of it. So if you are quite sensitive to blood, just put your hands in front of your eyes and it will be okay. So first, let's start with the motivations of the project. So as you may already know, cardiovascular diseases are one of the leading causes of death worldwide with cancer. Some of those pathologies directly affect blood vessels, such as the biggest artery of our body, which is the aorta. And some patients can have an abdominal aortic aneurysm, as you can see here. This is characterized by a dilatation, abnormal dilation of the aortic diameter, and that can reach like more than 100 millimeters for the diameter. And this is due to several factors such as smoking, diabetes, hypertension, etc. I'm not telling this, it's not because you are smoky that you will have a blood clot, but it can be like due to this. So, and it has been shown that in most cases, like around 90% of the cases, that there is a formation of an intraluminal thrombus, so this blood clot, inside this abdominal aortic aneurysm. And you can see like the scale bar, it's something that can be reached like this. So it's something very huge, okay? From a biological point of view, this is an aggregate of cellular elements, red blood cells, platelets, etc., that are nested in a fibrin network. From a mechanical point of view now, this is a multi-layered, inhomogeneous, highly inhomogeneous porous structure with permeability gradient. Spoiler, like disgusting picture. So here, this is like a real like human blood clot, okay? And here maybe you cannot distinguish a bit about like the different layers, but there's three distinct layers, here like the red one called the luminal, then the medial and the abdominal layers. And basically, the main objective of my PhD is to understand the role, the effect of this blood clot on the evolution of aortic pathologies, because actually we don't know.
What's the size of it?
So this is like millimeter paper, okay? So it's something that is something like this. So this is something huge, okay, in your body. So this is basically like fill the entire like aortic aneurysm, okay? But there is still blood flow. There is no clogging, okay? There's still the blood flow can pass through, okay? There's no clogging. That is the reason why most people that they have this, they don't know about it. This is asymptomatic. So if we look into the literature, we can find a wide range of permeabilities. Concerning the microstructure, we have only 2D microstructure provided by histology. I will explain you later what is histology, and we don't have any information regarding the 3D microstructure. Concerning the mechanical properties, this is biology, so this is highly patient specific. And concerning the numerical modeling, people doing some numerical simulation on this kind of pathology use very simple model. So this is sometimes isotropic elastic model, and we know that this is not the case. Or sometimes few more complex with poro-elastic and poro-hyperelasticity. So we clearly have a lack of experimental data. So our method is to provide both morphological and mechanical characterization at several scales using two different ways. The first one is the mechanical way, using in vitro permeability studies and micro-CT. And you will see that doing micro-CT on soft biological tissues can be quite complex compared to rock. And then the biological way using histological investigation and all of those experiments in order to, at the end, build a relevant model. So let's start with the microscopic scale. So here, what is important to understand ILT permeability? So here you have a cross-section of a normal aorta, and here you have the blood flow and you have the cellular elements, and the cellular elements can naturally feed the vessel layer. But now, when you have an abdominal aortic aneurysm, you have now a complex porous media between the blood flow and the vessel layer. And we can ask several questions, how the cellular element can feed the vessel. we can also like think like how the cellular element can flow within the thrombus, and is like this thrombus responsible of that we call rupture of aneurysm, meaning like the breaking of the vessel. So to answer this, we built a homemade permeameter setup in order to have the microscopic permeability. So basically, we first like cut a sample, okay, for a specific layer, and then we place it inside a chamber. We put like water inside at a specific height to have a constant pressure, and then with the pressure difference, the water will flow through the sample if this one is free per mole. It's something very easy, and then we can, using Darcy's equation and considering that the thickness of the thrombus is much smaller compared to the height difference, we can have this very easy formula and calculate the permeability. So we did this for the 3 different layers, and what we observed is very interesting, is that both medial and abdominal layers were not fluid permeable, no perfusion, compared to the specific layer called like the luminal layer, the one close to the blood, that there is a wide range of permeabilities comprised between 10 to the power minus 18 to 10 to the power minus 14 meters square. So it's something very interesting that there's only one layer that is fluid permeable. And the wide range of permeabilities can be explained by the fact that this is biology, so we have a lot of inhomogeneity. So I tested like 11 samples from like 11 patients. So that is the reason why we have like differences. So those results are consistent with histological findings that I will just show you a little bit later, but not with some permeabilities found in the literature with the work of Bocchetti, who said that all of those 3 layers were fluid permeable. And you will see that it's impossible. So let's move with the microscopic characterization. So we perform histological investigation at Latimer Hospital. Okay, so basically histology is like you cut a small piece of the sample, you place it inside something that we call a cassette for paraffin and bending, and then we have like a very thin slice, so around like 4 microns, with the tissue on it, and then we can put some stain, specific stain. So the CD61 is in order to bind platelets, and HE in order to bind red blood cells, fibrin, etc. And then you can visualize under a microscope, and then we can obtain those kind of results for the thrombus. Here, like for the CD61, here in brown, this is like the platelets. So we perform quantitative and qualitative analysis. Okay. So if we first like take the first layer, the luminal layer, the one close to the blood, we have this kind of structure. So this is a very highly porous. We cannot see here because we have like a lot of cellular elements inside this. So here, like in dark pink, this is the red blood cell, and here, like in blue, this is the white blood cell. Okay. If we move like a little bit above with like the next layer, we have like the luminal one, and we can see that the structure is like totally different. We have now more condensed structure, okay, that create like larger pores, okay, and we, like in this specific layer, we don't have like cellular elements. And this is something interesting, and if we move to the external layer, so the structure is like totally different. We only have now like oriented fibrin fibers like this, very condensed, without porosity. That is the reason why it's impossible to have perfusion. So then we perform like quantitative analysis, okay, for like a specific layer. And then what is interesting to see is that here, like the majority of the cells are present in the luminal layer, so the one close to the blood. So to conclude on it, we can see that the cells can navigate inside like the specific layer that is the one close to the blood, so this one, the luminal layer, and not in like the medial and the abdominal layer. But the main problem is that with this kind of technique, this is only 2D microstructure, okay? And this is very aggressive for the tissue because we have to fix the sample, to fix the morphology, to remove the water, etc. And this is something very aggressive for the tissue. And this is only 2D. This is something very important. That's the reason why we decided to build an experimental setup in a micro-CT in order to have the 3D morphology. But when we are like studying soft biological tissues under X-ray, this is complicated because there's no contrast. Okay, so we have to prepare the sample in order to have contrast under X-ray. That is the reason why we use this protocol. So basis is a fixation in order to have fixed the morphology, then the dehydration process, and then use the stain in order to, when we put like the X-ray on, can see that we have like a contrast under X-ray. And then after like several hours of acquisition, I think it's around 3 hours, I think, we can have those kind of results. Okay, so this is like the 3D morphology, okay? And if we make like a section, we can have like here the different structures for each specific layer. And you can distinguish, I mean, if it's like, okay, distinguish like the structure of the luminal layers, like highly like randomly like oriented fibers that create like very small pores compared like to the medial layer and the abluminal layer. So we did some quantitative analysis using HiMorph software, which has been developed by my co-supervisor in order to perform quantitative analysis on porous media. And what is interesting to see is that the porosity for the medial and the medial layer are like very close. But the main difference is the mean pore diameter like is around 9 microns for the luminal layer, and it's around like 30 microns for the medial layer. And the other thing is like the mean distance between the pores are like very smaller for the luminal layer compared to the abluminal layer. That means that there is more chance to have perfusion for this layer. Then we really wanted to use these results in order to calculate the microscopic permeability. So to do this, we build porosity map. So this is the porosity map of the first layer. Each color here corresponds to a specific connected pore network. So here the turquoise is only one pore, I mean an interconnection of pores over the whole thickness. And if we have like an interconnection over the whole thickness, we can calculate the permeability. So to do this, we use HiMorph software as well. So it's basically like resolving Darcy's equation in pore network modeling. And then we obtain those results. So, and we have like the macroscopic results in the range of the macroscopic results. So we were happy with this result, and then we did exactly the same for the second layer. And here that you can see is like the structure is very different. We only have now regions of interconnected pore network, but not over the whole thickness. That means that there is no perfusion. So it matches also that we found at macroscopic scale. So that is nice, but for this kind of protocol, I use like kind of the same protocol for the 2D histology. That means fixation, dehydration, etc. So this is something very aggressive for the tissue, and we really want to like to maintain the physiological properties of the sample. So we develop a new experimental protocol. So the same here, but like we remove the fixation and the dehydration process, and we change the stain by another one called SPT, which has been shown that it can maintain the physiological properties of the sample. So after like several hours of acquisition, we obtain like kind of the same results, okay? But now like we have like a little bit less contrast, okay, compared like to the previous stain. And we compared like the results, the quantitative data from like the PTS or the previous stain and the new one, so the SPT. And what is interesting to see is that for the pore diameter and the mean distance between pore, there is smaller and closer pore, okay, using this new protocol because there is no alteration of the tissue, okay? So if we preserve the tissue, we can validate, okay, those data in this new experimental protocol. So this is like the very, like only those data are like the first in the literature concerning this kind of blood clot. Then we really want to do exactly the same thing as the previous protocol in order to calculate the microscopic permeability, and we observe exactly like the same range of magnitude, and did exactly the same for the second layer with the middle layer with no perfusion. Okay, so then, so detailed 3D microstructure, that's what I said. Then a little bit about like more biomechanics. So we really wanted to understand both microstructure deformation and the mechanical properties. So to do this, we built a compression setup that will be placed inside the macro CT, okay, in order to have, that's what I said, the deformation and the mechanical properties. So basically it's like an actuator here that can, this is linked to the 3D printed rod with a load cell, and then we can apply with the computer like different range of compression. So the main objective is to perform that we call stress relaxation compression test. And how it works is like something very easy. So we first perform a reference scan, that means without any compression. Then we perform, when we have like the rod that touch here, like the sample, we perform like a 40% compression, okay, and leave it for like 1 hour. This is called like the relaxation. Because during compression, this is soft biological tissues, it will like expand a little bit during like, several minutes. And it's very important to have no movement during microcity acquisition. So after the 1 hour acquisition, 1 hour, relaxation, we will make a scan, so the second one. And then we did exactly the same thing at like 60% compression, and then we obtain those kind of curves. So this is like very like typical curve, okay, from those kind of tests. Here, this is the time, and PK1 is like the pure Kirchhoff stress. It's basically like the force divided by the cross section of the sample. And this is for 40% compression and 60% compression. And we can see two different behavior. The first one is the viscoelasticity that can be seen by here, like the relaxation of the sample, as you can see here and here. This is the first one. And the second one is the non-linearity. Because the relaxation will depend on the amount of compression you will apply on the tissue. This is called like the non-linear viscoelasticity of the sample. And then in the same time, we can obtain those kind of images at like 0, 40, and 60% of compression. To be honest with you that these images like looks nice, but it's very, very, very noisy. And I'm struggling to like post-process those images actually. I'm trying to improve those imaging. Now let's move to the last part, which is the image processing validation. Because I think this is something when we are using microcity, it's something very important. So here, this is my sample over there. And which segmentation is the best? This one or this one? I cannot answer this because I cannot like compare my results to some in the literature that we can have with rock. If we have like sandstone or something like that, we can compare like the range of permeabilities or porosity. Here I don't have anything. So I look into the literature and I found like different papers, okay, that use synthetic images in order to validate their segmentation process using a toolbox called Astra Toolbox available on MATLAB and Python, okay? So here, this is like the virtual images of a rock, and then using Astra Toolbox, they can generate microcity artifacts, basically like reproduce a real microcity experiment. And at the end, they have like all of the parameters for the ground truth image and then use different segmentation in order to validate their processing. So basically, it works using like two different algorithms. The first one is called the forward projection. It's basically to simulate like the X-ray that can pass through a sample. So here in my case, like my sample or the rock, if you have. And then it generates like a sinogram, which is like a succession of projection. And then we have the filtered back projection here. This is basically use the generated sinogram over there in order to reconstruct the images with the microcity like artifact. So we did this, okay, for our sample. So here, during my experiment, I have like microcity slices, and then I can extract a grayscale histogram. So this is something very easy, basic. Here in red. Then virtually, I can generate a stack, okay, of porous images with like the same range of porosity size and permeability. Okay, so I know everything on those images, and then I can, using Astra Toolbox, like put the microcity parameter of my experiment. I mean, the distance between the source and the sample, like the number of projection, etc. And then I can obtain the first one, the raw images here in blue. Okay, and if I want to be like more relevant, I can add during the tomographic reconstruction some noise, real noise, I mean Gaussian noise, Poisson noise, blur, etc. to have noisy images here in green. Then I can extract those histograms, and then basically what we want to do is like to have a virtual histogram in green that match the experimental histogram here in red. And that's what we did, okay? Because if we don't add any noise, you have this grayscale, okay, here for those images. So it is something very important to add some noise to be more relevant for the grayscale histogram. And then we have now the possibility to test several segmentation techniques, and then at the end to validate which one is the best. So, to conclude, okay, on my presentation, so we show that some qualitative and quantitative analysis using histological images, and we developed a new physiological, microcity protocol to perform like quantitative analysis, and this is something interesting because it has not been done yet, okay? Then, for the mechanical investigation, we developed like an experiment in order to have both the mechanical properties and the images of the deformation. And then finally, we developed an image processing validation because sometimes it missed in the literature in order to validate our segmentation technique. For the perspective, actually we are in the blue configuration. That means we need a stain in order to have contrast under X-ray. And we really want to move to that we call phase contrast imaging. This is something very nice for soft biological tissues, such as blood clot. And basically, we really want to go to the synchrotron, okay, in order to have better contrast. We don't need to use a stain, and the experiments are very fast. Only a few seconds or minutes, okay, compared to actually it's like more than 3 hours for an acquisition. So basically, what we want to do is like to go to the ESRF, so the synchrotron in Grenoble, okay, to perform two experiments. The first one is to put our macropress inside the synchrotron and perform what we call 4D fast imaging. That means to have in the same time the deformation and the mechanical properties. So 4D for like 3D, okay, plus the time. And the other experiments, a little bit tricky to develop. So we have our 3D morphology. And we really want to 3D print this. This is like quite complex. And then perform something that we call particle tracking velocimetry. So this is the video of Tom Bultres from Ghent University. We did this for rock. So basically it's like to put some tracers, some particles inside the water and flow inside this sample, okay, in order to understand how the cells can navigate within the different structures here. Thank you for your attention. If you have some questions, I'll be happy to answer.
Questions? Yes.
Thank you very much for the very nice presentation. So I was wondering if your sample was wet, like you have fluid inside the sample, because the PDF you showed the frequency, you have several peaks on the original data, the blue one.
The blue one, for which experiment?
You had this curve of the histogram.
Oh, okay.
So I was wondering if those peaks are related to the fluids you have.
You mean this one? Oh, sorry. This one.
Yeah. That one.
So yeah. So actually, this is due to two things: the fluid inside, because during the microcity, okay, this is not in air. I put some fluids inside. This is called DMEM. It's like PBS, okay, so saline solution with glucose, etc., nutrient, okay, in order to keep the sample like wet. This is something very important, okay, and yeah. This is due to this first one, and the second one is that due to the stain, because like with this stain, this is like very complicated, like sometimes to distinguish between porosity and the tissue. This is basically due to these two tips.
So it's fully saturated.
Yeah.
Okay. I don't know how.
Fully saturated. It depends of like if the layer that you are interested in, like the flow can pass through or not.
Okay. Yeah, I don't know how much you have time in your patient, but I highly recommend the neutron imaging because
to use
neutron imaging. If
yeah.
You can
That's we are planning to go, but like doing experiment on human sample can take time to have like papers, authorization, and stuff like that. Yeah. But yeah, we wanted to do this.
So you know what is the mechanism behind this? You have different porosity for different levels, for this luminal medium one.
Yeah, so basically it's like when you have like your vessel like this, you will have the blood flow here, okay? So this is like the formation of the blood clot. So here you will have like the different cells, okay? And then here, due to the change of the structure, you will have like here an increase in velocity, okay? and then it will activate some platelets. And then here you have like recirculation area, and then those activated platelets will be stuck here, okay? And with time, you will have like a growth of structure, and then with time, it can be something like this, and then you will have something like this. And with time, you will have delamination. So that is the reason why we have like a lot of cellular elements here, okay? And nothing there, because at the end, like in like years, you will have no cellular elements, like it will be die, okay? So the structure is highly dependent of like how the blood clot is like forms.
So you say that the flow affects the porosity of this?
I think, yeah.
I'm quite curious why you are looking at improving the segmentation and not the reconstruction. Because from what you showed, you are just using FDK, like a feedback projection. What
Yeah.
are you looking at?
I mean, after like the acquisition, I have like these images, okay? And basically, in order to have quantifications or quantitative data, I can have to perform like segmentation, okay? But I can say, okay, I will use this filter, or this filter, but I cannot like validate if like this is like the perfect filter for this kind of images, okay?
No, I'm not talking about filters. I'm talking about different algorithms for reconstruction.
Yeah, okay.
So that will impact image quality quite significantly. I think more than segmentation.
I mean, I try to, because you know, like this kind of images, like complicated to have like image processing. I really wanted to try different segment. I mean, you thought about segmentation, right?
No, I'm talking about reconstruction. So from the projections that you get from the CT machine.
Yeah, but I'm not like regarding like the projection, etc. I would just explain what is like behind the aneurysmal box. That's it.
Yeah. If
And I don't know if I understand. Yeah, sure, okay, perfect. Yeah.
Very nice presentation. Is there a way to do any of this in vivo? Without having to go to the synchrotron?
I mean,
the synchrotron is
doing X-ray in vivo, like it's a little bit complicated.
Is there
But there is,
complementary?
yeah. Some people are doing MRI, okay, but they are doing MRI in order to have the mechanical properties in vivo, okay, but they cannot like have a very nice morphology. It's impossible. So, but there are some improvement with like the imaging processing, and then they're trying to. They can like actually have the mechanical properties with MRI in vivo. Yeah, there's like several papers on it.
Last question?
Yeah. So in that diagram, you mentioned the flow apex where your clotting is happening. So in the previous lectures, we have seen, especially when you have the bifurcations, we do see those recirculation zones exactly at the bifurcating locations. So can you say something about that? What are the preferable locations of the clotting?
I mean, like in all patients, it will be like this. But I mean, you can have like several geometries. So here, this is like you can have a structure like this. You can have structures like this. You can have structures like something like this. So it depends of the morphology of the aneurysms, I mean itself. And then the flow, like how the flow will impact like the blood clogging, it will depend highly on the morphological structure of the vessel.
But the flow is not steady, it's always pulsating.
Yeah.
So it's not the normal streamlines that you get.
I know, yeah.
Okay, let's send Joyce again.